let's try to solve this example. So please make a pause of this video and please read this statement carefully and think about how to solve this problem. Okay, so let's do it together. So now we have an energy system that is proposed by someone, and now that has a heat exchanger and turbine. And this turbine is adiabatic. So let me just make a hatch lines to represent that is adiabatic turbine. Now we have air comes into heat exchanger, and this heat exchanger we have certain heat input Q. Okay. Then okay, so let's say that at T1 is 300 Kelvin and P1 is 5 bar or 500 kilopascal. Then we have certain heat input to the heat exchanger, and at the exit of heat exchanger we have temperature at 500 Kelvin, and the pressure is a little smaller than 5 bar to 4.9 bar, so we have 490 kilopascal. And this air goes to turbine and it does certain work, W. And after expansion of this air, it leaves at the ambient condition. So now T3 is 298 Kelvin and P3 is 1 bar or 100 kilopascal. So it's basically a dead state. So now you try to evaluate this system. So please comment on the feasibility of this proposed system. And if you don't think that can happen, then please explain why. Right. So let's try to solve this problem. It does have two components. One is heat exchanger and the other one is turbine. So let me try to solve heat exchanger first, then move to turbine. There are certain assumptions that we can make. The first assumption is air is an ideal gas. Okay. And also constant Cp and Cv. And from the given K value and R value, we can calculate Cp and Cv. Okay, that is 1.005 kilojoule per kilogram and Kelvin. And now Cv is 0.717. Oh, okay, let me just, there is a 1.004 and 0.717 kilojoule per kilogram Kelvin, right? And what is our other assumptions? So let's ignore change of potential energy and kinetic energy, okay, of air, ignored. Then third assumption we can make is, well, that is already given in the statement that turbine is adiabatic. Turbine. And also that is in steady state. Then let's try to calculate Q first. So that is heat transfer in to heat exchanger per unit mass, because we don't know the mass flow rate, right? Okay, so let's assume that your mass flow rate is 1 kilogram per second. Then we can draw your heat exchanger, and that is your control volume. And we have Q in. Now while we have M dot 1, M dot 2, okay, obviously that is same as M dot. Okay. So now let's assume that that is 1 kilogram per second, and in order to satisfy the steady state condition, it also should be 1 kilogram per second. Then, how can you set up the first law of thermodynamics? Is that open system or closed system? So that is open system. Okay, and now we can write up the open system for the first law for the open system. In that case, the changing rate of the internal energy of your control volume, which is heat exchanger at this time, should be 0, and that is because of Q. Okay, and okay, so now let's try to write it in the entire equation. So now Q dot minus W dot, which equals to 0, and now we have M dot H1 minus H2. Okay. So now Q, that is heat transfer in per unit mass, which is Q dot divided by M dot, that is H1 minus H2. Because we already assumed that specific heats are constant, then this equation can be written more simply as T1 minus T2 times Cp. And let's try to input all values that we already have, Cp, T1, and T2. It gives us the value of 200.8 kilojoule per kilogram. Okay. Then how about turbine? Okay, let me draw the turbine again. That is adiabatic. Now we have 2 and 3. Okay, and now we also can write the first law of thermodynamics. So 0 equals to Q dot, which is 0, minus W of the turbine, and plus M dot H2 minus H3. So small w, which is the work output per unit mass, is Wt dot divided by M dot, right, can be written as H2 minus H3. Again, that is Cp T2 minus T3. We know all values, so by using those values, we can see that the work per unit mass becomes 202.8 kilojoule per kilogram. Okay. Now, does it make sense or not? Can you really make that system as claimed by one crazy engineer? What do you think? How can you tell whether or not that is possible? Okay, what I would do is I would evaluate that Q and W to calculate the thermal efficiency of that system. Again, that can be defined as W divided by Q. Okay. Then, by using those numbers we already calculated, the thermal efficiency for that case becomes 1.10 or 101%. Now, is it really possible? That is even, more than 100%. And from what we learned today, we cannot make any heat engine that has thermal efficiency of 100%. Now, this person even claims more than that, 101%. So, what you can say is simply, no, that is not possible. Okay? Because, again, we cannot make thermal efficiency more than 100%. Well, 100%. That is a violation of the second law of thermodynamics. Okay? So that is the end of this example. Thank you.